his presentation, but I can certainly jump in. Hello, everybody. Glad to see you joining us. Thanks for checking in.
Yeah, sounds like you're getting quite a few folks in.
Yep, sure are. Yep. Okay.
Okay, I think yeah.
All
that
right.
was weird. I had another window open and then it just flipped out on me.
Well, we are broadcasting now, Bill, and I think we've made a decision. Let's go ahead and get started, even though the main presentation isn't quite over yet, because we've got a lot of people that have joined us.
Okay, I'm gonna. I guess I'm first. Let me share my screen and we'll get going.
By the way, guys, nice shirt.
We do look.
Hey, we want to be in style.
Sure.
And while we're getting the presentation up, for those of you, you're obviously already using the chat. Don't know if we're going to be monitoring the chat as much as the Q&A channel. So if you do have some questions, why don't we go ahead and use the Q&A channel, and we'll address them.
Okay.
And, yep, Bill.
Can you see my screen?
Yes,
can you see my screen? Okay, very good.
Yes.
Well,
yes.
I got put in the enviable position of following an astronaut as just a dirtbag bomber pilot, but I'll do my best to keep this interesting. And just want to talk a little bit about the competition rules part, and then Steve will go over stuff on the DTEG, and then Tony will follow up with whatever he wants on safety. So let's get started. I am the director of rules, and let's talk about the rules and requirements. And I want to address two different things. The first is kind of the intent behind these rules and requirements, and the second is addressing the two questions that got asked over and over again in different forms on HeroX. So we shall get going. Okay, so the intent is, that we are the world's premier engineering rocketry competition, with a stress on engineering, doing things purposefully to, and so it's more than together a rocket and, going out and having fun in the desert. And so, at a meta level, the three things that judges are really looking for is, that projects have kind of a unified design vision and execution, that you're actually looking at a specific target, you're actually trying to do a certain thing, and you're designing your rocket in such a way as to make that happen. We should see conscious decisions on each piece of your project. In other words, not just taking pick your airframe or fin because it's a standard piece or something like that, but actually deciding we need our fins such and such because of the altitude or because of the stability we want to see. And then the other thing we're looking for, obviously, since this is an engineering competition, is some hands-on engineering, the ESRA components on the part of the teams. And so here's some examples of things that we've seen in our review reports about why people did it. So that's what the team did last year. We're going to make it. It's going to work this year. Teams working at cross purposes to themselves. This is a standard part. And the other thing is overemphasis on somebody's pet. And so if the team did that last year, can you do it better? You need to at least address. Second thing, cross purposes. I've seen this multiple times where one part of the team is working on optimizing drag to cut the drag down on the rocket, but the rocket's already overshooting the target altitude. So there's a disconnect between what the parts of the team are trying to do. Standard part. most of you have the ability to make your own airframes. Why not make a 5-inch airframe? If that's what suits your project. And then, like I said, sometimes you see overemphasis on folks' pet projects. I saw one report where they talked about parachute design, and the rest of the report was only 10 pages. So, that's, there's an obvious disconnect in what people want to see. Here's a slide that I just put together looking at the predicted altitude and the rail exit velocity for all the stage 2 entry reports. And you'll see that the intersection of those two lines are your 10,000 foot desired altitude and your 10,000 feet and your 100 feet per second velocity off the rail. And you notice that pretty much no matter what motor you're using, you've got teams basically all over the place where you've got, teams slow off the rail and sometimes so slow that, it's really questionable whether a rocket like that will be stable. Or you have teams that are wildly either overshooting or undershooting their designs. And so one of the things, what that tells me is that, where teams are not necessarily designing to reach a certain thing. They're just designing a rocket and then, okay, yeah, we hope it gets to 10,000 feet and, we'll accept whatever we get out of that. And so, and in the future, I'd really like to see those, those projected values getting a lot closer to the target rather than spread out all over the place. Okay, one last thing on writing your reports and doing your projects. Don't make the judges guess. Okay, that the requirements for the technical report are pretty well spelled out, and the judges shouldn't have to hunt around to see if you've got a weights and measures appendix. They shouldn't have to guess about what your process was for selecting components. They shouldn't have what your reasoning is. And so, this engineering project is communicating to the people who are going to evaluate, meaning us, the judges, but in the future, that would be your bosses, customers, that you unambiguous that you are actually answering the questions that they need to know. So very quickly, got lots and lots of school participation letters. Really, if you think about it, the purpose is to just show that everyone that on to the competition is actually part of the school or is graduated within the last year. The reason we don't want to, have people hiring, your local AAA guy to build your rocket for you, and so we want to make sure that there's no unfair advantage here. So everybody coming to the competition needs to be on the letter. If you have other members of the can't come to the competition for some other reason, you can add them or you can leave them off. But that's your option. Okay, enough on that. And a contentious issue, especially when we thought we were going to have an actual physical competition, was the lash up with the AAA Rocket Association. The thing that drove this, well, two things drove this. One is to really tie into the premier rocketries in the world to tap their expertise. Also bring people in high-powered rocketry hobby. But the second thing is that's really because the insurance for this kind of event is almost impossible to find nowadays, and the insurance that the Spaceport has and everybody else has does not cover the teams. And so one way to solve at least part of that problem, especially for the solids teams, the ESRA and COTS teams, is to have them be part of AAA. They need a level 3 to be there. So that means if you don't have a level 3 on your team, you may need somebody in the, and actually reimburse them for traveling out there. We are all volunteers. There's no paid staff. So, this is all on time, and you'll get a lot better result if you actually can support you. And so you also have to AAA members, AAA student membership's $10, so that's not too bad. And hybrids are not covered. You're responsible for your own insurance. We are exploring some avenues, at least for hybrids, and so that may change by next time. That AAA insurance only provides coverage for the COTS and ESRA and solids. And if you're a solids team, then you're going to need to comply with the AAA rules. You're going to have a mentor. I would highly suggest getting somebody on your team level 3 qualified. That would best, but bringing in experience can really help you out. Okay, so that is all I have from the rules perspective. To answer questions after Steve and Tony get done. Okay, over to you, Steve.
Steve, we can't hear you.
Steve, I think you're muted.
Yeah, I'm trying to unmute him, and oh, there it goes. There it goes. It's showing now.
I went through I switched 12 different sorts of microphones, but we're good now, right? Okay, sorry about that. Thanks, Tony, for noticing that. Okay, this is really it's kind of an FAQ because it's again, it's the questions that we see most often, and then it's also by looking at the technical reports that the areas where I think you guys need a little bit of guidance. So let me move ahead here, and I just want to draw your attention to a number of talks that we have over in the experts track. There are some very relevant topics that I'm not going to cover because we have a whole session on. So Jim Jarvis is going to present about really construction techniques and methodology for rigging your parachutes and deployment exercises. Then we've got the GPS requirement, which was new a couple of years ago, but still a little bit of questions about that. Chris Harris is going to have a discussion so that we handle every single one of your GPS questions. We have Greg Deputy, who's going to be talking specifically to those who are doing the SRAD solids and really simulating those, because as one of the things as reviewers of your projects, we're going to need to know the KN and ISBs and the different parameters that are going to be around some of the formulas that you're working with. This year, more than any other year, we've gotten some discussion about the 3D printing of rocket parts. We got Ken Biba, who's going to talk specifically about that fabrication methodology and making it relevant to rocketry. And then the last one is really for some of your advanced teams who are looking at doing the liquids and hybrid rockets. We've got a team of our experts that are going to be there to handle a roundtable discussion. So we try to make these sessions very relevant to what you guys are experiencing. So I'm going to go through our philosophy a little bit on this on the DTEG, which is the Design, Test, and Engineering Guide. We recognize that first and foremost, it's an engineering competition. It's something that we want you all to think about. We want you to be able to meet some parameters that we provide you, but we're really interested in how well you take that set of small amount of criteria and fabricate something that's going to be exciting and new, and exercise your minds and exercise your your team skills. So we're not looking to dictate. We are looking to guide. So it's the engineering guide, right? So want to make sure that you get your engineering muscles flexed during this exercise. And like I mentioned, it's the innovation. It's the innovation around the components that you fabricate. It's the there's the standard stuff that you can buy off the shelf and put together, and that does require engineering skills. But we're really looking to see how well you accept this challenge and how you're really able to manufacture some of your own designs. And I guess that's what we're trying to do too, is to give you the hands-on experience. I've run into a number of engineers, and I've got a son-in-law, my daughter. They're both engineers, and the practical hands-on stuff is actually a little bit challenging for them. So they're very book smart. One's in aerospace and one's in structural engineering. You think that would be a great marriage, and it is from my standpoint, although I didn't orchestrate it. But the practical side of this thing is what we're looking to do is get you your hands on and get your hands dirty. And we encourage a multidisciplinary approach because, listen, you've got electrical engineers, you've got computer engineers, you've got structural guys, you've got mechanical guys, you've got, all the multidiscipline, all the different disciplines that you can apply to a rocket, including your financial department, including the, social media, so communications, really looking to build a team around this project so that, again, you get that experience of, in the industry, we don't work at a project and do it from nuts to bolts. It's all subsystems. It's all, the subgroups that you work with that make your project successful. Now, having said all that, we're going to err on the side of safety, and a lot of this discussion will be around safety because, we have a potentially very dangerous activity that you're all endeavoring on, and based on our experience, we're going to make sure that this thing is going to be safe, and that's why we've adopted the Tripoli rules so that we can follow the Tripoli safety code. So first FAQ is around electronics, and that's genuinely where we get an awful lot of our questions. And so I want to just cover DTEG section 6.8, which is around redundancy. And we're looking for completely independent systems. They should be able to function on their own so that one point of failure is not going to bring down two systems. We have a lot of people in the past that have engineered things around using a single power source or a single switch, or, yes, you have two altimeters, but if you have a single point of failure, which is either a switch or your power source or your energetics, we'll cover that as well. They have to be two completely independent systems. But they don't mean identical. So for instance, you can have your own ESRA electronics, your COTS electronics. They don't have to be the same set of electronics nor the same set of deployment methodology. They just have to be separate, that can work independent of each other and can deploy your parachutes. And it doesn't mean simultaneous. So we have a lot of teams that say, yeah, I've got a primary and I've got a backup, and they're both due to fire at apogee. That's not what we're looking for. We want to make sure that you have a primary system that's capable of doing the job, and you wait X amount of time and you decide whatever that is, but then you go ahead and you fire the backup just in case the primary didn't work. So it's not simultaneous. It's give the first chance, give your system a chance to work, and then if it doesn't, the backup should be able to help it. And then I'm going to say this at every step is test, test, test. There's a number of ground tests you can do. There's a flight test you should do. There's a number of tests. So you want to make sure before you come to the spaceport that you've had an opportunity to field test your electronics, field test your deployment. If not, just, backyard test, I'll call it, which is to make sure that, if you're not flying it, you're doing the ground testing of your systems. Move on to redundancy around your electronics, and why we require a commercial off-the-shelf product is because those are proven. We all fly the Stratologers and the G-Whizzes and the Ravens and Telemetrum stuff. So not to say there can't be a failure in those systems, but they are flight tested, they're battle hardened, and they're well used in the hobby. So that's why we require one of your independent systems to be a commercial off-the-shelf system. Right now we have, you can get your electrical engineering team to build your set of electronics, which we encourage. Just have that backup. The other thing right now for this year, and we'll review it again for next year, but we're saying that the commercial off-the-shelf kits, because you have to do the soldering, we excluded from the COTS category this year. We're looking to review that, and we'll see if it maintains that. But right now, it was commercial, and then you can do whatever you want. Okay. Now, in terms of deployment, okay, so you've got your independent electronics. Now you got to fire them. So black powder is primarily the system a lot of folks use. A couple of caveats here. So your primary system, the amount of black powder you use, which you should have tested and know that that will blow your nose cone off. But the backup you use, you want to make it whatever you used in the first one plus. Because you want to make sure that, listen, if that first one didn't work, it wasn't because something has got pinched, or is there a, some sort of force that when you put your nose cone on, it stuck something and it didn't come out. So when you have a primary go off and it doesn't work, make sure your backup is more energetic. The other caveat here is for the folks going to 30K or higher, you want to make sure if you're using black powder that you're getting what you expect, okay? Because on the ground, you're doing it at 1 atmosphere. When you're flying high, black powder behaves a lot differently. And I'm referencing a paper here done by Jim Jarvis, who's one of our high altitude guys, and he's done a great job in an experimental method, showing you that at some of those altitudes, only 10% of your black powder is going to go. So at any rate, read that. Make sure you understand how black powder behaves, or any of these systems behaves at high altitudes. Moving on, CO2, same principle. If you got a 16-gram, CO2 cartridge, make the next one 20 or make it 25. But if there's no harm in your backup system being more energetic if your primary system works, right? So you could just be blowing out, an open tube. So don't be afraid to make your backup a little more energetic. Jolly logic chute release. Don't do it. Just don't do it. We've had it's not designed for large parachutes and the rockets for the weights that we have. So just don't do it. And there's not, so at any rate, we're excluding that from the competition, and I don't expect that to change. Tendered centers, you want to use them either in parallel or serially, and you don't want to have two matches going into one powder well, right? You want to have two tendered centers, either serially linked together or in parallel, so that if one system doesn't blow, you have a backup system that will blow an alternate tender to sender. So again, two E-matches in one charge well is not backup. That's not an independent system. And the reason I express this is because these are questions that we get routinely and that we address every year. So cable cutters are fine. Bigger parachutes require a bigger cable cutter. And you want to make sure that you've got redundancy in your cable cutter so that if the first one doesn't cut, you've got another one that's in serial that will cut the cord. Mechanical. So really nice. I'm going to go back to 2019, and one of the teams, international teams, had a really nice pneumatic system that would, when it had apogee, the pistons would go up and it would mechanically push off the nose cone. Well, there wasn't a backup, and that system failed. And so when we talk about redundancy on deployment, if you have a mechanical system, there's no problem with having a black powder system to back that up. It doesn't have to be another mechanical system, but you want to make sure you've got a second pathway for that parachute to deploy. And again, test. We would like to see video. We like to see the test on the ground that you're using to demonstrate that the system works. We also don't mind seeing videos of any other experiments that you have that are relative to having these things work together and independently. Switches and batteries, another frequent topic that we get questions on, because when we're doing our reviews, we want to take a look at your system, your switch system. And it's fine for using mechanical or screw switches or pull switches or key switches, but you want to make sure that you look if they have a G rating, because some of them will work fine in smaller systems. You got to understand the amount of G's that you're pulling and what the effect is going to be on your switch, and what orientation your switch is in. There's the pull switches, and if you pull the switch and you're not oriented correctly, the force will actually close your switch. So make sure, and we've seen all this. This is all experience talking. So listen and take these notes to heart. Magnetic switches are fine now. AAA has sort of rescinded some of you need a mechanical interruption in the energetic before you load it on the pad. So magnetic switches are okay, but let me tell you my experience with a magnetic switch was I had a Leatherman or a knife on my belt, and I had my magnet attached to my belt. I'm carrying my rocket out to the pad, and it armed my electronics. So, if you have one of those magnetic switches, make sure that the person carrying the rocket isn't the one that has the magnetic switch. Wi-Fi and Bluetooth, also acceptable now. Make sure you understand what the battery life is going to be. Sometimes you can be on the pad because somebody's got a problem with something else, and that's not just for your deployment electronics, it's for your cameras and your GPS, and understand what the battery life is, because that's going to have an impact on, we've had rockets that have sat on the pad that their batteries went dead. That means there's no juice to your electronics. Make sure they're accessible. Make sure that the less ladder work you have to do next to a rocket, the better off you'll be. Understand that sometimes that's not possible, but think about access panels and think about access to where you're going to arm your electronics. And last place you want to be is next to a rocket, and there's something that happens that launches the thing. So think about your access, think about and plan about how you arm your electronics and do it safely. Shunts is actually, I referenced this. This is another tip from Jim Jarvis, who is part of our ESRA team and has done a lot of high altitude and two-stage work. He has a methodology where he shunts. Now, he'll arm his electronics with a Wi-Fi switch, but he'll have a shunt in between the switch and the energetics. And then when he's far enough away, he's got a magnet externally on his airframe that he'll pull a string, and it'll make sure then that the circuit is completed to the energetics from the flight computer. So that's a worthwhile exercise to look at, and Jim's done a lot of thinking about this because he does a lot of two-stage work, and he's on a ladder or trying not to be on a ladder. Last thing he wants is the rocket to launch while he's on a ladder next to it. I mentioned a little bit about battery life. Think about where you are. You're in the New Mexico desert. It's 110 degrees outside, and that 110 degree with the sun is going to be beating down on your electronics bay. Batteries don't behave real well over 140 degrees, at least the LiPos don't. So you want to think about that engineering challenge and how you could prevent some of that. Like, don't paint your rocket black. Okay, you don't want to absorb a lot of that energy based on just the color of your rocket. So think about the access and think about the location, because you want to be able to change the batteries easily if you have a battery that drained because you were on the pad too long. Just all things to think about. And we've had rockets that, again, have come in ballistic because the battery died. We've had rockets that we had to do a rapid depressurization on because of battery's death. So that's one element that I think we could see a little more thought around. Okay, material selection. Got a lot of questions about stainless steel this year. The standard sets, section 8.3 says you can't use it on any load-bearing structure. And that, two reasons. One is that it's not as strong as regular steel, and the other is that it's frangible. So if you can't build your airframe, you can't build your motor case, can't do anything with stainless steel along those lines, because if it KOs, it's shrapnel. And want to make sure that we stay away from that from a safety standpoint. And but you can use metal in your fabrication. Just make sure that it's aluminum, aluminum alloy, that you can make airframes and fins, and you want to make if you're making your own motor case, you want to make sure that it's done out of aluminum. I put in there copper alloy because that's another ductile, non-frangible metal, but I've never seen a copper rocket. So, but I put it in there because it's a potential you can use it. The last bit again is on stainless steel in your eye bolts or your swivels or your U-bolts, and the rationale here for this rule, and it's a rule, so it's something you had to follow, is that it's not quite as strong as steel. So we may revisit, we look at the DTEG and we do, based on what our experience has been and what sort of questions you have, we'll take a look at that. Launch parameters. This is another one we see an awful lot of teams not necessarily doing very well at. So we're talking about, you're in the New Mexico desert. I had never been to the New Mexico desert until 2018. And it's a different environment. If you hadn't done, and I live in Texas, so it's even different than Texas. So make sure that you understand the environmental conditions. Make sure you know the temperature, the elevation. The spaceport is almost a mile high. What the wind speed is. Take a look at June's weather records and say, what's an average wind speed, and put that into your modeling. The atmospheric pressure and humidity will have an effect on your altitude. So, and same thing with the elevation. So, we get models or simulations, and they're left at default for whatever system you're using. And you're using a 3-foot, in that simulation, it's a 3-foot rod with, I think, 59 degrees or, maybe 50% humidity, and that's not the environment you're in. So, Bill, I love the work that you did with the graph that showed, motors and what predicted altitudes are and what speed off the pad is. It shows you that an awful lot of you, it just empirically looking at that graph, 50% of you aren't meeting what we like to think of as our safe parameters. And then, so the other thing is our launch pads, we have 17-foot rails. And we recommend that everybody doing a solid is able to get the rocket off on a 17-foot rail. We're not anxious to, or we won't extend our rods, based on your selection of your motor. So you want to make sure that you're able to do it in this window, 17-foot rails, and our launch angle is going to be 5 degrees away from crowd. So make sure that you put that in your model. And then I can't recommend enough that you do a flight test, because in order for you to meet the altitude requirement, this is a competition, there's a lot of aspects to it, but if you're in the 10K and you're shooting the 16K, you're not doing something right. You want to make sure you understand what your motor performance is. You want to make sure that you understand what the coefficient of drag is, so that you're able to tune things to the point where you're within 5% of the target altitude. So departure rail velocity, 100 feet per second. We're using that as our rule of thumb for a safe and stable flight. And if it's below that, we want you to prove it, either by a flight test or you've done some mad modeling to make sure that, and you've thought of all your parameters and you think that this long burn, low initial thrust motor is what you need for your rocket. You know, we'll give you a fair amount of pushback and a fair amount of questions to ask you to justify that. Ascent stability, you know, a body, a caliper and a half or 2 calipers is really the sweet spot. That's where you want to be. That's for a good, safe, stable flight. Anything over that, and you know, we're gonna want you to justify that from a engineering standpoint of why you couldn't meet the metric, because there's a fair amount of wind out in New Mexico, and if we've got a rocket that's overstable, you're not going to meet your altitude, goal, but you're going to end up with a recovery that's going to be miles away. And listen, if you drift over to the White Sands Missile Base, you're going to lose your rocket because they're not going to let us onto the base, maybe within the time frame that you're looking to get out of there. So make sure it's stable. And you've used the parameters that we've put in our guideline, the DTEG. And this last little bit here, and it's a provision inside the DTEG that says, you know what, we're going to change it. There's going to be new technology. The 3D printing is a perfect example. You know, or different, better switch technology, better battery technology. So we got at the end of the year, we're going to take a look at all the issues that we had for this year, and we potentially will do a revision on the design, test, and engineering guide. So to that end, I'll say, feel free to reach out to us because you know, we're showing you what we're seeing from our side, and you may have stuff that you can help us or that you've seen that might be useful incorporation into next year's competition. So there's the addresses for us here on the call. We handle the design, this document, the design, test, and engineering guide. We handle the launch operations out of the spaceport. We handle the range safety out of the spaceport, and we do the judging. So this is the team that, if you have suggestions to, we're the guys that you want to give these recommendations to. So with that, Tony, I'm going to throw it over to you and let you go ahead and continue on with any sort of safety issues that you want to address.
All right, thank you, Steve. My name is Tony Alcacer, and I'm the Range Safety Officer for Spaceport America. I think this is my 7th or 8th year participating, and I was able to attend some of the original launches in Green River, Utah. Some of my background is that I've been into high power rocketry for about 25 years now. I do a lot of research motors. I make my own body molds and stuff. So I've done quite a bit. And the first IREC competition that I attended was a very big eye opener to me in the lack of rules and the lack of successful flights. And I was nervous just being there. And so over the years, we've come up with quite a few rules. And when we talk about having a new rule or changing rules, it's not a single person. It's a group of high power people that have been in this hobby for a long time, making up a decision. And one of the things that kind of is always in our background is we do not want to stifle the invention or the mechanical engineering aspect, etc. What we do with the rules is we want to have as safe an event as we can. And so some people will see that we require 100 feet per second exit speed, which is higher than NAR, which is higher than Tripoli, and ask why. Well, if I'm flying a Estes rocket on a C5-6 motor and it's a little bit slow coming off the rod, not a big deal. But if it's a 110-pound rocket flying off a 17-foot rod in 30-mile-an-hour winds, it's a big problem. We'll close down the range way before the wind exceeds 20 miles an hour. So some of our rules in place seem excessive, and they're there for a reason, whether it's from the location that we're at, for the size of rockets, or et cetera, that those rules have been in place. And like the use of Jolly Logic shoot release and stuff, that's for a model rocket. When we saw two of them rubber band together on a 25-foot parachute on an 8-inch hybrid rocket, we stepped back and thought, this is inappropriate for what we're trying to do and stuff. So each of the rules that we change or come up with is just to make things safer. You know, the forged eye bolts and all that stuff, that's in there for a reason. I could switch and show you an eye bolt that has opened up. Why not spend $3 extra and get the next bigger size eye bolt and make sure that it's forged? You know, and I'm going to pull up one picture here, I hope. Is that on your screen? No?
Not yet.
Maybe I'm doing it wrong. Well, anyway. So, you know, one of the questions we have is designing the recovery system. And we see anything from 1/8-inch Kevlar that's 8 feet long that has a couple of 200-pound quick links on it. And is that good enough? No. And if I had to tell you how to design your recovery system, design it so that it holds together when the rocket comes apart at max Q. Max Q being the fastest part of the flight, usually towards the motor burnout. Because if all those major parts hold together, your parachutes are going to shred, that it comes down in one section and most of the major pieces are still together. Your rocket's never going to go straight up, stop, chute will come out, and it comes down and lands in a bed of marshmallows. That will never happen. So always design to the worst case scenario. The best recovery shock cord that's common is 1-inch tubular nylon. It's got some stretch to it. It's easily purchased. And then go from there. Attach it to the hardest known point, which is usually part of the motor. And then if you use quick links, the picture I was looking for is a picture of a quick link that's rated at 3,200 pounds, and it takes up most of the palm of my hand. And so you would need 2 of those quick links to keep that same 4,000-pound safety rating. Why do you need that quick link? I'm sure you can figure out or look up a knot that's much more capable, much quicker to tie than, you know, expelling the weight, the cost for a couple of quick links of the appropriate size. So, you know, that's about it. That Steve and Bob did a good job. Or Bill, sorry, Bob. Sorry, Bill. Pulling this all together. Are there any questions from any of us?
Yeah, I've been answering a lot of the questions as they come up. So you guys may want to take a look at the question section and see if anything you guys want to add comments to.
Okay.
Really good questions, by the way, everybody. They look good.
So far, Andy, it looks like you did a reasonable job answering.
Except for Peter. Peter, you're killing me, man. All right, so we have Isaac Sims who commented in there from Australia. Are you one of the Sydney guys, or are you from one of the other teams in Australia? I know you can't talk, so just if you get a chance to put in a comment. But guys, go ahead and toss out your questions. You got 4 of the leading senior people within ESRA from the flight and range safety and flight operations side right here, as well as the master of all judges and rules. You're not going to get this opportunity very often, so you can ask whatever questions you might have.
Thanks for kind words on my YouTube channel.
So what's a small fish?
Speaking of that, if all the attendees that are on here have not done this, Tony has a fantastic YouTube channel. T-Fish, what was it again?
T-Fish 38.
Yep, T-Fish 38. A slew of videos of tutorial videos that, I mean, every time I'm doing tip-to-tip fiberglassing, I pull up his video just to refresh myself with how it's supposed to get done. But tons and tons of other videos out there on almost every topic of high performance, high power rocketry. So if you're not subscribing, that's definitely an ESRA recommendation. Again, Tony's forgotten more about high power rocketry than I'll ever know. And let's see, you don't have to quite shake your head so fast, but anyways, that's why he is in this wonderful role. And I do my best just to keep him out of all of the non-technical stuff.
Not to spin this session, but the latest video I did was on the things that we're looking for on the flight safety reviews. And tomorrow, I think at 11 a.m., we're going to have a session on how to survive that, how to what to look for.
So somebody on the chat session has posted your YouTube channel, Tony, and
Okay.
Peter says that the channel actually jump-started their composite production. And I actually remember the first time I met Tony, I told him he helped me with my level 2, and he didn't know it. You know, I glassed the tube and did tip to tip, and it was all with Tony's instructions. So.
Thank you for that. And the stuff that I learn, whether I learn it or it's a crash from my friend or somebody else, I try to pass those things on so that they're not as expensive or not hard or emotionally to suck it up and stuff. And so it's hard to do those videos. It's hard to do this and talk to a screen. I love talking about rockets and stuff. And so that it takes a little bit of getting started to do those YouTube videos and then running off at the mouth in between doing things and stuff. So
actually interesting. Peter just posted a picture of using Jim's methodology for rolling his carbon fiber tubing too. So
I do have a comment for Julian. Julian, I've been watching you. I've been replying to you. On your next tube, instead of starting your fabric on the bottom of your mandrel, try putting it on the top and wrapping it the opposite way. You'll get a tighter weave and you'll use a less epoxy.
Well, there you go. I mean, that's worth $5 right there. All right, guys, we're at 11:52. Again, the sessions will be recorded. You will be able to come back and watch it later on if you'd like. Again, thank you for joining us. We appreciate all the questions, again, except for Peter. But again, enjoy the rest of the event. And again, your participation is what makes this really great. Go ahead, Bill.
Yeah. I just you got a question from Tyler Douglas over in the chat channel about flying a P motor. And I think that's something that needs, I'm pulling up the relevant part of the rules and requirements, but that is something that we'll have to go through some detailed review on before you'd be allowed to do that.
If you post that question over on the Hero X forum and stuff, myself and Andy can pick that up and take it offline and figure out what they're trying to do and how to do it safely.
Now, one thing I want to add to that and Tony, and I think everyone will agree here. One of the big things that we look at every year during the registration process and the evaluation process is we look at how big of a project is the team attempting to create, to launch, to build. And then we go back and we look and we search and we research your team's experience, your past launches. I mean, if you've never launched a high power rocket before and you're going to start with a P, that's just not going to happen. If you've only flown one M motor at one Spaceport America Cup and you're going to a P, not happening. If you've never built an ESRA motor before, a composite self-built motor, not going to happen. If you have had some previous experience doing Class 3 waivers, going through the FAA and AAA review processes, that will help you. That will say, okay, they've got some experience. Again, a P motor is a major jump. I mean, that pushes you up in the Class 3 side from the FAA side, and that is a major evaluation. We've had 5 or 6 different teams come to the Spaceport Cup that over the years that have wanted to fly P motors, and every single one of those projects failed to show up. And so I'm not saying it can't be done. What I'm saying is keep your projects within the scope of your team's experience and expertise. If you come forward with a P-class motor and you don't have a mentor that is recognizable to the 4 of us, you know, somebody that is a legend in the rocketry community, it's probably not going to happen. If you're not doing it without a mentor, it is almost definitely not going to happen. So I'm not saying you can't do it, but you better have your ducks in a row well before submitting your application for that.
All right.
Hey guys, we got one question on there. Does anybody want to jump on there for that one?
I don't know that I'm getting.
You have to click on the QA on the far right.
Yeah.
And then click on open.
How do you feel about Molex? Use connect ejection charges to avionics bay.
To me, the more connections that you have, the more chances of failure. It's best to go from your electronic device eMatch all the way into the black powder. That way you don't have a whole bunch of different connectors.
Well,
was that applause?
I like to think so. Oh, there's Andy just put the applause on.
All right, everyone, thank you so much. And we'll move on to the next session. And again, have a wonderful time at the virtual cup. And I'm still pinching myself. We got this thing off the ground. And we'll definitely see you next year. That is absolute.
Fantastic. Bye, all.